Alrighty, let's go ahead and get started. And we're going to talk about properties of logarithms because there's uh, logarithms are incredibly useful, but there's a lot of ways that we need to know how to like use them and how to manipulate them to be able to be, well, more useful for us. So we've got, I'll say first that thing that we should probably talk about is we should probably talk about a couple identities. Now, the first thing that I always like to discuss when we're talking about identities is, of course, it's really important to know what a logarithm is. And I believe we covered that in the last video when we were talking about how basically what a logarithm is. But it starts basically with an exponential expression. So say I've got something uh, like y is equal some base number to the x. So this would be an exponential form. Now, I usually say, okay, well, log base b of y is equal to x, because what we're this basically says we're taking this base to a power, and that's going to be our answer. Well, if we're looking instead for the exponent, we could say, well, that would be a log base b of y is equal to x. So this is the exponential form, and this right here is what we call the logarithmic form. Logarith, I can spell. This is the logarithmic form. So this is one of our first sort of ideas of let's talking about the different formats and what these things are. Now so notice that on both of these, the base is the same. The base here of the exponent is b. Here, the base of the logarithm is b. And it's just here we're noticing that when I take this logarithm, the answer is an exponent. Now let's take a look at a couple other identities. And one of those is if I've got b to the log base b of x, that is equal to x. So basically this basically highlights that a logarithm as a logarithm is essentially the opposite of, well, it's basically like the anti-operation of an exponent. So think about like if you square a square root, it makes that go away. Same thing happens here. If I take an expo if I take put a logarithm in the place of an exponent, and the bases are the same, the answer is just going to be that exponent. And this is relatively easy to spot, but well, anyway, let's move on to, so this is our first identity that we usually talk about. And with this, of course, we've got to have just one thing that always has to be the case is this is that x has got to be greater than 0. Because I couldn't take an exponent and end up with a negative number. The next one that we are going to use is, well, if I've got log base b of b to the x, this is also just equal to x. So here, since, like I say, if we're asking, okay, what power on b will give me b to the x, it's just x. That is a relatively easy thing to say. Here, there is no real qualifier for what for what these things have to be. I'll just have to say that, x is real. So these are a couple identities, and these are useful for us later on. But let's talk about our three main properties, and I might throw in a fourth one there. But the first one is our product rule. The product rule for a logarithm is that if I've got a log with a base b of a product, so let's just call it x times y, this is going to be equal to the log base b of x plus the log base b of y. So that is going to be incredibly helpful for us if you ever need to, like, if you need to sort of parse a statement, if you need to sort of break up, if you need to separate out variables that you wouldn't normally, otherwise be able to separate. Next, we have our quotient property. And this is interesting because here, again, we're dealing with, well, if a product is, a product, we've got x times y. Here, we're going to have x divided by y. So we're dealing with a quotient. We're dealing with division. And in this, we've got, again, it starts with that log base b of that x. But when I'm dividing, I'm going to subtract. So basically, whatever is in my denominator is going to be subtracted. So I've got log base b of y. And now for our last regular one, we have what we call the power rule. And this one is incredibly useful. I find myself using this one all the time. So here, again, if we've got a log base b of x to the n, this is going to be n times log base b of x. So we're here, this exponent will turn into a coefficient in front of the logarithm. Now, we do have kind of I'll say there is another property, but it's one that it's, it is quite useful, but it is a little bit unusual. And it's what we'll call the change of base property. Now, with this, a change of base, I could rewrite anything. For a lot of things, and what I find myself using the change of base for most often is I want to know how to evaluate something on my calculator. But say I've got log base b of x. Well, I could rewrite this as log of x over log of b. And as long as I've got a consistent base for this other thing, so this could be, so I could use, I'll just say, call that log base a instead of b, which means that if I decide to use common log, I could use common logs and evaluate whatever this would be. Or if I wanted to use a natural log is, of course, a logarithm with a base of e, and it's usually written ln as opposed to log base e. But yes, so these are our main three, or these are our main properties that we use. And like I say, this mostly gets used if we're evaluating things. Sometimes this right here gets used when we're like solving equations. And these kind of identities can be helpful for us in other things. But these three properties right here, our product rule, where the a product in that logand turns into the sum of logs, a quotient where if I've got a quotient in my logand, or as my argument in my log or my logand, that'll turn into the difference of logarithms. And of course, the power, so if I've got a power in my logarithm or in that logand, that power can just become a coefficient. This means that we can do some really, really interesting things and use this to expand some expressions. So let's talk about using logarithms, using those properties to expand expressions. And wow, that I think my part of what I had kind of wore off there. But tell you what, let's do let's think about something here. And I'm going to show you, I'll show you an example, and then I'm going to show you my method of looking at this. So my first example here is this. Say I've got something like a log base 3 of 5xy all over z. Well, I want to expand this expression. And with this, I'm going to note that I've basically got one thing up here, one kind of expression divided by another. So I can just immediately divide, or where I think of this as division, which means I'm going to look at this as subtraction. So I'm going to separate this out and say, okay, this is going to be log base 3 of that 5xy minus a log base 3 of that z. So now I look at this and I see, oh, I've got my numerator and I've got my denominator. So anything in my numerator, that's going to be plus. This is in my denominator, that's going to be minus. And when we think about this, I will be able to break this out, and I'm going to let you in on a little secret right now. If I wanted to, I could, and this is my own mental process, so I'm going to do this in a little thought bubble. But typically, I usually skip this particular step. If I'm looking at just this and say, okay, this log base 3 of that 5xy, well, if I were to think, oh, that's 5x times y, that's going to be log base 3 of 5x plus my log base 3 of y. And sure enough, I can do this again right here and say, oh, this itself is going to turn into log base 3 of 5 plus a log base 3 of x. So notice that for every single thing up here, this just turns into, it's just all added together. So each of these factors is going to have its own basically basic term. So when I look at this, oh, this log base 3 of 5xy is going to turn into log base 3 of 5 plus log base 3 of x plus log base 3 of y minus, so still have this in my denominator here, that log base 3 of z. So notice that if it's in the numerator, each of those factors is added. If it's in the denominator, that factor would be subtracted. Now, if I take this a step further, we can also add in some information about what happens with our exponents. So let's show you what would happen if I have something where I've got some different exponents. So let's do this. I'm going to do log base 7 of x to the fourth y cubed z c to the 10th. And once again, I've got three things multiplied together. So I'm going to split this up into three different logarithms just to start, but then you're going to see something else fun happen. So This is our second example here. So when I do this, now I've got, oh, log base 7 of, that'll be x to the fourth, plus log base 7 of that y to the third, and then plus log base 7 of z to the 10th. And now notice that now we get to use that property where I'm bringing down these exponents as coefficients. So this first term is going to become 4 log base 7, or 7, of x plus 3 log base 7 of y plus, now this exponent is 10, so that's going to be plus 10 log base 7. 7, I keep wanting to put something else in there instead, of a z. So notice that the exponents become our coefficients, and it's still, I'm only writing each of those once. That's all. Or so I've got I've got powers of x, y, and z, and I'm going to end up with that log of x, a log of y, a log of z, and those exponents are just turning into the coefficients on those particular terms. So here is what I do. And I think you'll probably like how this works out. You're going to, when you rewrite, you're going to identify your different factors. And what you can literally do is if it's in the numerator, then you're going to end up adding that log. If it's in the denominator, you're going to subtract the log. And each of the exponents on those is going to become a coefficient. Exponents will become the coefficients for those. I can spell. Okay, I am apparently decaffeinated at the moment. So yeah, become coefficients of those. So, coefficients of those logs. So I'm going to do something a little bit tricky just to show you how quickly and how smoothly this actually works. Say I've got log base 2 of x to the fourth over the square root of y and then the z cubed. So I see I've got x, y, and z, and I'm going to point this out right now. I'm also going to remind folks that a square root is the same thing as having like y to that would be like a fractional power. So square root of y is technically like y to the 1/2. So here's what I mean. I've got three different factors. I've got a factor of x, a factor of y, and a factor of z. So I'm going to just break this out. So I've got this log base 2 of x and my power, and that is 4. Now, for my second one, where I've got the square root of y, that's in my denominator. So I'm going to subtract that. I'll leave myself a little bit of space here for that. I've got log base 2 of my y, and my coefficient here, like I say, the power on that y is technically y to the 1/2 power. Z is in my denominator, so I'm also going to subtract that. So minus, and I'm going to have that log base 2 of my z, and the exponent on that z is a 3. And with that, I'm done, and I'm done in one step. These, this idea of being able to break down a a complex logarithm into something like this is incredibly helpful. It'll be very useful. And you're going to see this a lot more once you get into some things like calculus and other things, but you're going to run into that later. Now, let's keep keep going. And now that we've decided to pull things apart, let's show us how we put things back together. But once again, this idea of our exponents turn into those coefficients. If it's added, if it's added, it's going to end up being in our numerator. And if it's divided, it's going to be in that denominator. So if it's subtracted, those are in the denominator. Let's take a look at how we can use something to combine terms now. So let's, oops, actually here, using properties of light to rewrite as a single expression. And yeah, let's say we've got something like 2, I'm going to do like log base 8 of A plus 3 log base 8 of B minus, oh, I'll even be mean. I'll do 1/3 log base 8 of C. But look at this. I've got 1, 2, 3 different expressions. 2 are added, 1 is subtracted. So these 2 are added. And if we wanted to do this, if we wanted to take this slow, we can do that. And tell you what, I will do this the slow way first. So first things first, I'm going to take these exponents, or these coefficients, and I'm going to move them up and make them into exponents. So let's say I do this. I do this log base 8 of A squared. This 3, I'm going to move up here. So this is going to be plus log base 8 of B to the third. And now I'm going to do minus, I'm going to keep this subtraction, but I'm going to move this exponent up. This is log base 8 of C to the 1/3. But I'm going to remind folks that, again, if we've got a fraction as an exponent, this is the same thing as, well, it isn't a square root since it's not a 1/2 down here. So this looks like, since my denominator is 3, this is going to end up being a cube root of C. Oh, these things are added? Well, go ahead. Let's just go ahead and make that a product. So this is going to be log base 8 of this times this. So this is going to be that a squared and that b cubed. Oops, minus that. Oops, a little bit out of alignment here, and now I've got one logarithm minus another. Let's put this all together into one. So I've got this log base 8 of, that's my numerator. So I've got that a squared b to the third all over the cube root of C, and we'd be done right here. And once again, if you are wanting to sort of move a little bit faster with these, you're welcome to. You can start to see, like I say, when you see these added together, so basically a positive coefficient over here, these terms are going to be in the numerator, and these are going to be the exponents. So let's try a different example. Let's do something like, I don't know, how about I do log base 5 of, I'm going to do something a little bit different. Oh, please, I hope you forgive me some of my background noise. I have some very excited birds in the room with me, in a cage, of course. Let's say I've got like x plus 2, and then I'm going to add to that log, or add to that like 3 log base 5 of y, and then I'm going to subtract from that 2 log base 5 of a of a z, and actually I'm going to have a z minus 1. And this one's a little bit fun because, okay, all of a sudden, yes, whatever this logand is, this is a single factor. This isn't broken up. This is just one specific thing. So now I'm going to say, well, here is my, so this is one factor of x plus 2, and it looks like you've got a coefficient of 1. Here's the other one. I'm going to have this 3 turned into my exponent for that y, so that's going to be y to the third, subtracted, which means this is going to be in my denominator, and this is that factor, so that's z minus 1, all squared. And all of this is log, log base 5. We're done, just like that. Alrighty. Hopefully this helped you make some sense of how you can use your properties of logs to like pull apart an expression or put it together. And we will see you in the next video.